So we've explained in a general sense how it is that regression models are fit, how you get a regression model from the data. And linear regression, like we said, is just a particular set of choices for each of these ways that we can specify a regression model. So when we're talking about candidate functions, we're just going to choose linear functions there. In order to grade our predictions, we use mean squared error. And in order to search the space of all these possible functions, we use gradient descent to find it. So none of this is stuff that you'll actually have to do, of course. This is all already implemented. It just helps to understand what it is when you get a regression model back. Okay, what are these numbers? How did the computer decide on what these coefficients are? So let's have a look now, not so kind of computationally, but what are you going to see in papers when people talk about regression? Let's just look a little bit about the notation. So for a simple linear regression where you have a single predictor, the notation you might see is something like this. So we have here mu hat of x. This is our predicted conditional mean at a value of x. And we're saying that is beta naught is what's called the intercept term, and then beta 1 is called a coefficient. Typically all of the coefficients and the intercepts are denoted with the Greek letter beta. That's just convention. It doesn't really matter. You can use alpha. You can use gamma. But if you see people talk about beta or beta coefficients, they're specifically referring to coefficients in a linear model usually. And you may also see notation like this. So y is equal to beta 0 plus x beta 1 plus epsilon. So this is just saying, okay, basically this is my prediction model here, and then here's some epsilon. This epsilon is a random variable that encodes the noise. So it's kind of saying like, okay, the way that y is generated is you give me the value of x, and then that gives me, here's mu hat. That gives me the mu hat value, and then I add to this some kind of noise, which gives me the distribution of y, whatever that may be. So you can always write it like this. It just changes depending on what your prediction model is. It will just change what this noise variable is. And we'll talk about a little bit more about this in a second. But let's just go on for now. Okay, so these things, beta hat 0 and beta hat 1, the definition of these things is that they are the minimizers of the mean squared error. So you may also see it written like beta 0, beta 1 hat are the minimizers, argmin, over beta 0, beta 1 of y minus, I'll put it like this. Okay, so what this is saying is over all possible choices of beta 0 and beta 1, so here I'm searching any possible, all possible numbers, the ones that I'm putting a hat over here, the beta 0, beta 1 hats are the ones that give the smallest mean squared error over all possible choices. So that's how these numbers are defined to be minimizers of the MSE, which we know that already. The question is, okay, I'm putting the hat over them to say that this is the kind of solution to that linear regression problem. And the hat we've seen before in the context of, for example, if I'm estimating like here it makes sense. If I'm estimating a mean mu, I'm going to call the estimate mu hat to show that this is kind of my best guess for this mu parameter. But the question here is, I put the hats on beta 0 and beta 1, which kind of implies that they are estimates of something. But what is it that they are estimates of? This is the question. And so in many kind of courses on linear regression, people start with assuming from the get-go that in fact this is the truth. So in fact that y is generated like in some kind of structural equation sense from some distribution that looks like this. So if you were to do the whole structural equations model, first you would have, you would also have x drawn from some distribution, and then epsilon drawn from some other probability distribution. And I'm writing this backwards, but you would first draw these variables and then say, okay, y is equal to this linear equation of x plus this noise term. And if you did have some data generating process that looked like this, then yes, if you did linear regression and you found beta 0 hat, beta 1 hat, then you could say, okay, well, this is my best guess for what that number is, and this is my best guess for what that number is. But this is crazy. I mean, why would you assume this? There's no reason that the true conditional mean function would be linear in general. We'll talk more about that later. Or even that these errors are independent from your covariates. So why would you assume this? The point here is that you can still get these beta 0 hat, beta 1 hat. These things are still perfectly well defined. Even without making those assumptions, I can still get these numbers, beta 0 hat and beta 1 hat. It's just that now they're not really estimates of a true value. I don't really actually have to care what those numbers are. What I care about is that this is an estimate of the conditional mean function. The beta 0 hat and the beta 1 hat, these coefficients, they are not actually estimates of some real coefficients, because in reality those coefficients don't exist, right? This is some linear approximation to the true conditional mean. And so that's just something to always keep in mind. But we are going to use these little hats here. I think they're still useful because they at least remind you that these things are random quantities. So if I had different data, I would get a different beta 0 hat. If I had different data, I would get different beta 1 hat. They depend on the data that we get, right? And then because of that, they themselves have sampling distributions. And even if those sampling distributions are not, centered at some true value that has any meaning, they are still useful to tell us other things about this conditional mean function, which we'll get to. All right, so all of this extends to cases where you have multiple predictors. So here I have x1 and x2 that are two different predictors, and I can do linear regression, and I can minimize the mean squared error of y minus all this stuff squared. And now I get three coefficients. So I got this intercept term, and I get the slope for x1, and I get the slope for x2. And this is the way it's written. You may also see it written like this. So if I have, so here maybe I have x1, x2, x3, x4, it's 5, so on and so forth. Then I don't want to write out all the terms individually. Often you'll see it like this. So you have the intercept plus some sum over xj. So here j is an index over columns, not rows in the data frame, but columns. So each of the predictors, and then beta j is a slope or coefficient for each of them, and you're just looping over that. And here I just write x with the little arrow over it to say it's a vector. If you're not familiar with vectors, that's okay. This is just an abbreviation, so I don't have to write x1, x2, x3, x4, or whatever, so on and so forth. And then if you're familiar with like linear algebra notation, you'll also see it written like this, where again here x, this is just an abbreviation for x1, x2, x3 when you have multiple predictors. And then same over here. And then this beta is a vector. It's kind of like all the betas stacked together, and you're multiplying. This is a vector multiplication, or a dot product, and you're multiplying each element of x with each element of beta. So it's kind of just writing this in a more compact way. And here you may ask, okay, what happened to the beta 0? Often by convention, people will just say, okay, x is a vector, but the first element of x is 1. So 1 times, so basically you can write this as like 1 times beta 0, and then you can just lump that 1 into x, and you can lump the beta 0 in with all the rest of the betas and write it like this. So that's just notation. So you recognize what these things are when you see them.